All right, George, I'm going to give it a shot again. So, looked at your first problem, and it appeared to be a position versus time graph. So this is my position on the y-axis, and this is my time. Now, I'm not going to work every problem word for word. I'm just going to give you some general information so you can sit back and study and figure it out for yourself, because then you'll know that you know it. All right, on a position versus, first of all, in any graph, anytime you see a graph, there's a ton of information there, but you have to really take the time to dig for it. So if you look at this one, it's a position versus time. It could have been velocity versus time. Could have been distance versus time. Could have been speed versus time. But you got to check out what is the x and y axes telling me. All right, so when I look at it, it looks something like this. And it flattened out. Then it got steep. And then it flattened out. And then it came down like that. And that one's kind of crummy. It's supposed to be straight. All right. So I'm going to call this one first section 2, 3, 4, and then 5. Well, 2 and 4 are going to be very similar, so we'll talk about them at once. 1 and 3 have some similarities. We'll talk about them, and then 5 we'll leave for the last. Okay, since it says position versus time, position is a distance with a direction attached to it, as opposed to just a plain old distance. This is called a vector quantity. I don't know if y'all have talked about that yet or not. You will. But a vector quantity is any physical quantity that is completely described by a magnitude and a direction. So a lot of kids freak out when they hear the word magnitude. It has 9 letters. It's a great word. All it means is size or amount. So if I ask you for the magnitude of your age, you're going to tell me that you're 15 or 16 or 40 or 109 or whatever you are. If I ask you for the magnitude of your weight, you're going to tell me that it's 185 pounds, 265 pounds, whatever it is. That number right there is the magnitude. Okay? If it has magnitude and direction, then we call that a vector quantity. You cannot call your age a vector quantity because there is no direction to age. So this is a scalar, S-C-A-L-A-R, quantity. This, however, is a vector quantity because it has magnitude, which is the 185, and then it has direction. Gravity is pulling straight down on that person. Weight is always pulling straight down. You'll learn more about gravity as you go through this course, but I just want to let you know that that is actually a force right there. Your weight is a force. And if you don't believe it, just push against Nicholas and see how long it is before he squeals, because you're exerting a force on him and it doesn't feel good. Okay? So this right here is a position versus time, so we're talking about all of these having a magnitude and a direction. So if you go back to your problem, let's say this is 10 meters here, and this is 2 seconds, and this is, let's go with 3 there, and then this one ends at 5 seconds, and then this one ends at 6 seconds. So I'm just kind of making some times up. All right. Well, what you're looking at is the slope of the line. First of all, you know it's a positive slope, so that means it's going in a positive direction. So your positive direction might be to the north. Your positive direction might be to the east. Usually when teachers teach physics, they do something like this. This is positive, because of the quadrants. This is negative, and this is negative. So if you remember from math, that's the first, second, third, and fourth quadrant. Okay, so north is going to be positive, east is going to be positive, south and west would both be negative. So this is going in some positive direction. It's a positive slope. Well, if I want to know the value of that slope, we know it's rise over run. So if we look at that, the way that I have this, it's a constant slope until it gets to the end of 2 seconds. I'm sorry, I'd call it the beginning of 2 seconds. So for the first 2 seconds, it traveled 10 meters, so the rise was 10 meters. The run was 2 seconds. and it's in the positive direction. How do I know? Well, I take the final position minus the initial. The final position is 10 meters. The initial is 0, so it's going to be 10 meters minus 0 meters over 2 seconds minus 0 seconds. And that gives me what is called the average speed. Or if VAV doesn't work, just call it average speed. And so the slope has a value of 5 meters per second, because that means that every second of time that passes, 5 meters of position has been covered. All right, so positive 5 meters per second, constant speed for that first 2 seconds. Okay, here, well, my pen will write, and here, there is no change in position. So for position 2, or 4, the slope is 0. So no motion occurred, just standing still. All right, that's all that's telling you, is no motion occurred. Okay, now I got to remember how to, this is the tricky part. Go back up a little bit. There we go. So no change in position occurred, no change in position occurred, so no motion occurred. All right. And then when I look at this number 5 right here, okay, so you can tell if I had drawn it good enough, you could have told, let's see if I can make that look any more like a, let's fix that. That's kind of crummy. Let's make it look like maybe that. There's a little bit better. Okay. So that's my 5th position that I'm talking about. So you can tell if it's moving away from and headed in a positive direction here, it's going back toward and headed in a negative direction there. So it's position, it's returning to the origin. So if I want the slope of that line, it should be negative, and it should be rise over run. So the rise, well, let's say that this is 20 meters and this is 10 meters. So the final is 10. The initial was 20. And let's say it took 1 second for that to happen. So the average speed for that situation is going to be negative 10 meters per second. And all that means is that it's moving at a constant speed of 10 meters per second in the negative direction. So if the positive direction was to the right, it's moving to the left. Okay? That's all that means. Not a big deal. All right, let's look at the second graph that she gave y'all. There we go. Okay, if I pull this up on my phone and look at that second graph, it is not a position versus time, it's a velocity versus time. That makes a difference. You've got to pay attention to the y-axis. So this is velocity versus time. And I'm going to call that meters per second. And this is time. And I'm going to say that it's in seconds. Okay, so the way that it looks like this, and then it's flat, and then it's flat. Now, all right, it slopes down. If you had thought this was a position versus time, you would have told me that he's just sitting still right here. Well, it's not a position versus time graph. It's a velocity versus time graph, so he has a constant speed. So you have to pay attention to what these say, or else you'll answer the questions wrong. Okay, so on a velocity versus time, several things. Direction is important. Slope is important. And then area under the curve is important. When you take calculus, which I guess will be next year, you will learn about integration and area under the curve for a function. When you take calculus next year, you'll learn about taking the derivative, and that'll be the slope of a function. So physics is very, very, very related to calculus, and it's really a very sweet relationship, but you've just got to build your self-confidence and make sure that you understand what's going on so that you can see the beauty of it. And you may not see it until you're older, but it's really pretty darn cool. Okay, so let's just say that this was 2 seconds. This was 4 seconds. And this would be 6 seconds. And we'll say that that ended at 5 seconds. Okay, so let's call this 10 meters per second. And we'll call this one 5 meters per second. And I don't know what value your teacher uses on that graph, but we're going to just teach you the general concept, and then you can go back and work on it. Okay, so again, positive slope gives you a positive direction, so you can say he's headed to the north or the east or to the right. Moving at a constant speed here, hasn't changed directions, just still moving at a constant speed, and then headed back in the opposite direction with a negative velocity. So let's take a look at the slope. So the slope is rise over run. So for this first one, he went from 0 meters per second initially to 10 meters per second, and it took him 2 seconds to accomplish that. So he had a change in speed of 10 divided by a change in time, delta t, 2 seconds. So he had 5 meters per second squared. So if he changed his speed over time, he accelerated. That's the unit for acceleration, and you just have to know that, but I want to show you where it comes from. So meters per second were the units in the numerator, divided by seconds over 1 in the denominator, in that denominator. So if I do this correctly, that's meters per second. Change that time sign to a times. So when I multiply meter times 1, I get meters, and then seconds times seconds gives me seconds squared. So that is acceleration, and it is positive. So his velocity is increasing in the positive direction. Okay? So be careful there. Now when I look at this one right here, he stays at 10 meters per second the entire time, and that lasts for 2 seconds. So that's his average or constant speed, and it occurs for 2 seconds. Now he goes from 10 down to 5, so let's look at this. So his acceleration, his speed is decreasing. So I'm going to say that delta V over delta T. All right, I want to do the final, which is 5, minus the initial, which was 10. And he still has a positive speed, it's just a lower positive speed. And that took him 1 second, so I'm going to say 5 seconds minus 4 seconds. So 5 minus 10 is a negative 5. Oh, this crazy thing, I keep messing it up. Negative 5 meters per second. All right, George, I don't know what's going on. I hope you're not laughing at me. It'll be okay. And that lasted for 1 second. So the acceleration for that interval is going to be a negative 5 meters per second squared. And all that means is his speed decreased by 5 meters per second for every second that he traveled. All right, now let's look at the area under the curve, because that's very easy. All you got to do is a little geometry. So if you look at it, here's a triangle that helps me understand or helps me pick out what happened in the first 2 seconds. So the area of that triangle is the area under the curve. Even though it's a straight line, we still call it the curve. Area under the function, whatever you want to, however you want to label. Well, the area is 1/2 base times height. The base is 2 seconds. The height is 10 meters per second. So 1/2 of 2 seconds is 1 second. 1 second times 10 meters per second is 10 meters. So that's the displacement, or the change in position, that distance traveled that occurred for the first 2 seconds. He traveled 10 meters. All right, now let's look at the next 2 seconds. So here's my curve, even though it's not curvy. That's my area under the curve right there for that second function. So if I look at that, distance 2 is going to be, well, how do you find the area of a rectangle? Well, you take the base, which is 2 seconds, and you multiply it by the height, which is 10 meters per second. So he or she traveled 20 meters during that situation. And then this last one, we know that, if I had drawn a little bit better, we have a rectangle and a triangle, so we're going to find the area of that, which is 1/2 base times height. The base is 1 second. The height is 5 meters per second. So that's 2.5 meters. And then this rectangle here is going to be 1 second long and 5 meters per second right there. Oops, 5 meters per second right there. So there are additional 5 meters there. So that person, while slowing down, covered 7.5 meters. Okay? So hopefully that will help you with the first two.